I'm Bob Tisdale. Thank you for taking the time to watch my presentation about the natural warming of the global oceans. It's a detailed examination of the sea surface temperature records for the past 30 years and the ocean heat content data since 1955. The causes of the warming are, of course, El Niño and La Niña and other forms of natural variability. This is not a theory. This is how sea surface temperature and ocean heat content data, not climate models, account for how they have warmed. The oceans cover about 70% of the surface of the globe. We know the surface temperatures of the global oceans have warmed over the past 30 years. There are satellite-based sea surface temperature datasets that do excellent jobs of measuring the surface temperatures of the global oceans from polar ice cap to polar ice cap, so we can rely on them. We don't have the concerns we would have with land surface air temperatures, like poorly sited surface stations, urban heat island effect, and land use changes. Those problems don't exist with sea surface temperature data. The other thing is, because the oceans cover so much of the globe, and because land surface air temperatures simply mimic and exaggerate the variations in sea surface temperatures, greenhouse gases they must warm the oceans for the anthropogenic global warming hypothesis to work. If the oceans have warmed naturally, then all bets are off on man-made greenhouse gas-driven global warming. Greenhouse gases then become an also-ran, a second or third tier climate forcing. They're then one of many land-only forcings. You might be thinking, now that's a big if, Bob. But if you'll watch this video, I'll show you that that's the case. A sneak peek. Did you know that the sea surface temperatures of the East Pacific Ocean haven't warmed in the last 30 years? We're not talking about a small region. The data in this graph runs from the south to the north polar ice caps and from the date line to the Isthmus of Panama. It covers about 33% of the global oceans. We can see they warm during El Niños and cool during La Niñas. Those are the large swings in temperatures. But in looking at the linear trend, they have not warmed in 30 years. A linear trend of 7/1000ths of a degree Celsius per decade shows that greenhouse gases have had no warming effect there. The models in the archives used by the Intergovernmental Panel on Climate Change, the IPCC, say they should have warmed about 4/10 to 45/100ths of a degree Celsius, or about 7/10 to 8/10 of a degree Fahrenheit over those 30 years. But they haven't warmed. Then there's the Atlantic, Indian, and West Pacific Oceans. Why don't we call them the rest of the world for simplicity's sake? We know the sea surface temperatures there have to have warmed because globally they warmed. Did you know this graph also indicates it warmed naturally? Look again at the graph. Do you notice anything unusual about the way the sea surface temperatures for the rest of the world warmed over the past 3 decades? Here, let me get rid of that trend line and do some color highlighting. The major El Niño events are shown in red, and the time periods before and after them are in blue, green, brown, and burnt orange. There's lots of things to notice now. The sea surface temperatures for the rest of the world only warm in response to major El Niño events. Notice how they don't cool in response to the La Niña events that followed those big El Niños. How can that be? We've been told that global temperatures respond proportionally to El Niño and La Niña events. That is, global temperatures are supposed to warm in response to El Niño events, and they do, and they're supposed to cool proportionally in response to La Niña events, and they obviously do not. I'll prove that to you in a little while. Now notice how the rest of the world's sea surface temperatures don't warm between the major El Niño events, the periods in green and brown. Do greenhouse gases make their presence known only during El Nino events and then sit idly by waiting for the next Super El Nino? Of course not. The only people who wait for major El Nino events are climate scientists, so they can claim global warming continues. Some of you have seen this GIF animation before. It's from the anthropogenic global warming proponent website, Skeptical Science. The animation is called Up the Down Escalator. It's an attempt to show that global land plus sea surface temperatures can flatten for a number of years, while overall there is a long-term warming. Well, they forget to point out that the recent flat period has lasted much longer than the others, and that it could be extended farther back in time than they are showing. Regardless, a similar animation appeared in the PBS special Climate of Doubt. It was introduced by Dr. Gavin Schmidt of the NASA Goddard Institute for Space Studies. Some persons have attempted to use this animation to cast doubts on my research. But this animation is simply an exercise in cherry-picked start and end dates. My graph is not. These are naturally caused, process-related upward steps. I will explain in this video the processes that cause these upward warming shifts. The up the down escalator animation also does not explain why the sea surface temperatures for the East Pacific have not warmed in 30 years. The presentation is broken down into 3 sections. First part, an introduction to El Nino and La Niña. It also includes discussions of why we saw those upward shifts and why we know they were caused naturally. Second, the long-term impacts of major El Nino and La Niña events on sea surface temperature. I just gave you a little preview of that. We'll confirm the reasons for and the timings of the upward steps. The third topic is the impact of El Nino and La Niña and other natural variables on ocean heat content. El Nino and La Niña explain all of the warming in the tropics, and the ocean heat content is also influenced by other natural variables which explain the known warming outside of the tropics. While the discussion is broken down into these 3 sections, the topics are so interrelated that you can't discuss one without referring to the others. So the initial discussion of ENSO provides much of the explanation of the warming of the sea surface temperatures, and it also supplies part of the explanation of the warming of the ocean heat content data, the warming of the tropics. Part 1 of this 2-part video series presents the first 2 topics, and Part 2 provides a discussion of the ocean heat content data. First, let's eliminate one point of confusion right at the start. El Nino Southern Oscillation, or ENSO, is the widely used name for the coupled ocean-atmosphere process that includes El Nino and La Niña events. El Nino represents the ocean portion of the name, and Southern Oscillation represents the atmospheric side. The term was first used in a scientific paper in the 1980s. Unfortunately, the use of the word oscillation gives the wrong impression to a lot of people. It did to me at first, too. El Nino and La Niña are not part of an oscillation or a cycle. This graph represents a commonly used sea surface temperature-based index for the timing, strength, and duration of El Nino and La Niña events. It shows the sea surface temperature anomalies for an area in the equatorial Pacific called the Niño 3.4 region. What stand out are the spikes in temperature of the large El Nino events and the dips in sea surface temperature of the La Niñas. But notice, there can be back-to-back and there can be back-to-back-to-back El Nino events with an ENSO neutral year, not a La Niña, between them. And there can be double-dip La Niñas like we've recently experienced. So the tropical Pacific does not cycle between El Nino and La Niña and back to El Nino. ENSO is not an oscillation. It does not cycle. El Nino and La Niña can be independent events, depending on the whims of Mother Nature. Another important point: an ENSO index does not represent the process of ENSO. The ENSO index only represents the impacts of ENSO on the variable being measured. That should be obvious, but this seems to elude people. In this case, it's the sea surface temperature anomalies of the Niño 3.4 region. It indicates the frequency, strength, and duration of El Niño and La Niña events, but it does not account for all of the processes of ENSO. It does not account for the preliminary portions of the ENSO process, and it definitely does not account for the after effects, as you shall see. Last preliminary point. We're discussing the sea surface temperatures for the past 30 years for a specific reason. The Intergovernmental Panel on Climate Change, the IPCC, says that only greenhouse gases could have caused the warming over the last 3 decades. But they base their beliefs on climate models, not on data. In their 4th assessment report, they wrote, Figure 9.5 shows that simulations that incorporate anthropogenic forcings, including increasing greenhouse gas concentrations and the effects of aerosols, and that also incorporate natural external forcings, provide a consistent explanation of the observed temperature record, whereas simulations that include only natural forcings do not simulate the warming observed over the last 3 decades. The data contradicts the IPCC. It shows the warming occurred naturally. For the discussion of El Niño and La Niña, I'm going to borrow the cartoon-like illustrations from Section 1 of my recently published ebook, Who Turned on the Heat? And I'll mix in some graphs and some animations. Why are we discussing El Niño and La Niña? It's important for you to have an understanding of the ENSO processes for you to be able to recognize that the global oceans have warmed naturally over the past 30 years. La Niña and El Niño are parts of the processes through which the largest ocean on our lovely planet, the Pacific, periodically creates warm water, then redistributes that naturally created warm water within the oceans and releases naturally created heat to the atmosphere. Always keep in mind how big the Pacific is. There aren't any superlatives that do it any justice. It stretches almost halfway around the globe at the equator. Its surface area covers more of the planet than the continental land masses combined. No discussion of ENSO is complete without an overview of the trade winds. The trade winds blow from east to west across the tropical Pacific. They are important for a number of reasons. The north and south equatorial currents in the Pacific are driven by the trade winds. But there is also a current that opposes and runs between them called the equatorial countercurrent. It's normally much smaller than the other two. It can grow quite large, though, during an El Niño. The trade wind-driven equatorial currents run into land and are forced to head toward the poles. They circle around and form what are called the North and South Pacific gyres. A quick note about the equatorial cross-sections that appear in many of the following illustrations. The dimensions are obviously way out of proportion. But even though they're skewed, it's important that they appear on the illustration. Under normal, also known as ENSO-neutral conditions, the sea level in the western tropical Pacific is about half a meter higher than it is in the east, and that's another effect of the trade winds. The temperature variations taking place below the surface of the equatorial Pacific occur in the top 300 meters, or roughly 1,000 feet. And then there's the width of the equatorial Pacific. It's about 16,700 kilometers. And again, that's almost halfway around the globe. Moving on to the ENSO process. First thing to discuss is ENSO-neutral conditions. That's normal conditions. It's not an El Niño and not a La Niña. Sunlight, very important, sunlight warms the waters as the trade winds blow them from east to west across the tropical Pacific. The warm waters accumulate in an area called the West Pacific Warm Pool. The West Pacific Warm Pool can be about 300 meters deep in places and can sometimes grow to the size of Russia or about twice the size of the United States. The warm water in the West Pacific Warm Pool is what fuels the El Niño. So to give you an idea of how much warm water is involved, imagine the United States covered in water up to 2,000 feet high in places. In other words, there's potentially a tremendous amount of warm water involved in an El Niño. I know you're thinking about man-made greenhouse gases right now, but please don't get ahead of me. The trade winds also draw cool waters from below the surface of the eastern equatorial Pacific in an area called the cold tongue region. And that process is called upwelling. As a result, under normal conditions, the waters can be 8 to 10 degrees warmer in the West Pacific Warm Pool than in the cold tongue region. The oceans release heat primarily through evaporation. The moist warm air rises in the west where the water is warmer, and as it rises it cools. The more the air rises, the cooler it gets, and as it rises and cools, it can hold less moisture. Eventually it comes out as rain, and in doing so it releases the heat from the sun that was used to evaporate it. That's the basic process through which the oceans warm the atmosphere. The trade winds replace that rising air. At higher altitudes, the air cools as it travels east, and then it drops down in the eastern tropical Pacific, supplying the air for the trade winds. And just in case you're wondering, that circuit is called a Walker cell. We're getting close to talking about El Niño. We've got to discuss a few more things about enso-neutral conditions first. Because the trade winds are pushing the warm water to the west, it piles up there. It's about half a meter higher in the west than it is in the east in the cold tongue region. Gravity. We can't forget about gravity. It would like the water in the east and west to be the same height. But the trade winds are holding the water at a higher level in the West Pacific Warm Pool. It's a balancing act. An important point. The trade winds create the temperature difference between the Pacific Warm Pool in the west and the cold tongue region in the east. However, it's the temperature difference that causes the trade winds to blow. The trade winds and surface temperatures are coupled. They interact. The trade winds and the temperature difference reinforce one another with positive feedback. And that's called Bjerknes feedback. Bjerknes is the gentleman's last name. B-J-E-R-K-N-E-S. Okay, now we're getting to the fun part of Mother Nature's handiwork. We've got that balancing act there in the tropical Pacific, with the temperature difference in trade winds versus gravity. What do you suppose happens when the trade winds relax due to a weather event in the western tropical Pacific? Now, there are a number of things that can and do cause the trade winds to weaken. A tropical cyclone, also known as a hurricane for those of you more familiar with that term, a tropical cyclone in the western tropical Pacific, or a couple of them, sometimes straddling the equator, can weaken the trade winds sufficiently and long enough for gravity to win the balancing act. Then the warm water in the West Pacific Warm Pool sloshes east, and that's how an El Niño starts. During an El Niño, warm water from the surface and below the surface of the West Pacific Warm Pool is carried east. The equatorial countercurrent grows much larger than normal, and the warm water is spread across the surface of the central and eastern equatorial Pacific, sometimes as far as the coast of the Americas. During the El Niño, more warm water than normal is on the surface of the tropical Pacific and that increases the sea surface temperatures there. The convection, the clouds, and the precipitation all accompany the warm water to the east. Because the warm water covers more of the surface, there's more evaporation, and therefore more heat is released from the ocean to the atmosphere. That heat is carried poleward, where it can be radiated to space more readily. That also helps to reduce the temperature difference between the tropics and the poles. To feed the rising air that has now moved east, the trade winds in the western tropical Pacific have become westerlies, and the trade winds in the east weaken. I'm going to give my voice a break for 2.5 minutes and insert a video from the NASA Scientific Visualization Studio, and the video is called Visualizing El Niño. Keep in mind that the presentation of sea level change in the video is greatly exaggerated. Other than that, it's a great 3D animation showing the interactions between sea surface temperature anomalies, sea surface height anomalies, and surface winds. Then they switched to a cross-section of the equatorial Pacific, showing the changes in temperatures there.
El Niño, the world's biggest climate phenomenon, returned stronger than ever in 1997. Satellite, ship, and buoy observations show the onset of this warming of the eastern Pacific Ocean as early as May. El Niño globally changes precipitation and temperature patterns, often with destructive results. Visualizing how 3 key data sets differ from normal conditions reveals the magnitude of the 1997-98 event and gives new insights into how the ocean and atmosphere couple to produce El Niño. First, we look at sea surface height. The gray sheet rises and dips as much as 30 centimeters from normal. Next, we map sea surface temperature. Red is 5 degrees Celsius above normal, and blue 5 degrees below normal. Finally, black arrows are added to mark sea surface winds. A weakening of the trade winds in the far western Pacific fuels an eastward moving wave. Sea level is raised as the wind-swept wave progresses. The wave's arrival at the South American coast reduces the normal upwelling of cold water and warms the surface by as much as 5 degrees Celsius. Intense atmospheric convection associated with equatorial ocean warming causes local winds to converge, abating the trade wind's strength and extending the warm pool of water into the eastern Pacific. Beneath the ocean surface, warm and cold waters are separated by the thermocline, a boundary at 20 degrees Celsius. El Niño flattens the thermocline, squeezing the warm bulge of water eastward into a long, shallow pool. As scientists collect more detailed data through efforts such as NASA's Earth Observing System, visualization will be crucial in probing the elaborate interactions and far-flung effects of future El Niños.
I'm going to borrow a few graphs from my book now to illustrate and confirm a few points. This graph illustrates the temperature gradient across the equatorial Pacific in December 1996. That's a year before the peak of the 1997-98 Super El Niño. A quick note. The reason I use 2 years to define the El Niño is because they typically start in one year and end in the next. Using both years avoids confusion. Back to the graph. There were end-zone neutral conditions in December 1996. Note how the sea surface temperatures in the west are much warmer than in the east. That confirms our earlier discussion. In this graph, I've added the December 1997 sea surface temperature gradient. Before the El Niño, the warmest water was in the west. During the El Niño, it's now in the central equatorial Pacific. but the greatest change in temperature occurred in the east. And we can confirm that with a graph of the sea surface temperature anomalies. Notice how little the temperature dropped in the western equatorial Pacific compared to the rise in the east. The warm water in the east obviously didn't come from the surface of the west, so it had to have come from below the surface of the West Pacific warm pool. We can confirm that using sea level anomalies. Sea levels in the west dropped a bunch, while in the east they rose a bunch. And we can also use ocean heat content anomalies to confirm that as well. Ocean heat content for depths of 0 to 700 meters cooled in the western equatorial Pacific while they warmed in the east. Note, while that data reaches depths of 700 meters, the variations along the equatorial Pacific are taking place in the top 300 meters. Let's move on to the transition back to enso-neutral. El Niño events typically peak in December, but there are exceptions. El Niño events are normally tied to the seasonal cycle. During the decay of the El Niño, the trade winds resume and push the warm surface water back to the west. This is the first map in an animation of sea surface temperatures, not anomalies, before the 1997-98 El Niño. We'll start the animation. The warm water, much of it coming from below the surface of the West Pacific warm pool, sloshes east, and then after the El Niño, the trade winds resume and push it back, with much of the leftover warm water remaining on the surface. And we'll let it repeat. Most of the warm water is below the surface before the El Niño. It sloshes east during the El Niño, where it's on the surface, and then it sloshes back to the west, with much of it remaining on the surface. There is also leftover warm water below the equatorial Pacific at the end of an El Niño. It is also returned to the west, but it's transported by phenomena called Rossby waves, and that's R-O-S-S-B-Y. Sometimes only one Rossby wave appears to form. At others, two show up quite clearly. The next animation is a small segment of a video that used to be available from the Jet Propulsion Laboratory. It's from their animation tpglobal.mpeg. It disappeared from their website, but I've uploaded it to YouTube. This portion of the animation captures the Rossby wave that carried warm subsurface waters that were left over from the 1997-98 El Niño, traveling from east to west at about 10 degrees north latitude. If we look at the upper right-hand cell, we can see the Rossby wave forming at about 10 degrees north, west of Central America. You'll see it carried leftover warm water from east to west. Watch what happens when it reaches Indonesia. It's like a second El Niño taking place in the western tropical Pacific during a La Niña. Do the sea surface temperatures of the Niño 3.4 region account for that leftover warm water that's below the surface that bypasses the Niño 3.4 region? No. And the sea surface temperature data of the Niño 3.4 region also does not account for the leftover warm surface water as they're blown west after the El Niño. An ENSO index, all ENSO indices, only indicate the effects of ENSO on the variable being measured. They cannot account for all of the effects of the ENSO processes, especially the after effects. The leftover warm water is then carried poleward and into the Indian Ocean. That is, it's been distributed from the tropical Pacific. La Niña conditions are next. They're simply exaggerated enso-neutral conditions, but they play an important part in the enso process. The trade winds are stronger during a La Niña. This causes more cool water in the east to be upwelled, so the cold tongue extends farther to the west than normal. And the stronger trade winds push the West Pacific warm pool farther to the west. With a warm pool farther to the west and with the stronger trade winds, there's less cloud cover over the tropical Pacific. This allows more sunlight, known in scientific terms as downward shortwave radiation, to enter the tropical Pacific and warm it to depths reaching 100 meters, though most of the warming takes place closer to the surface. The additional sunlight provides more warming than normal to depths of the tropical Pacific Ocean. This allows the La Niña to replenish the heat that was emitted by the El Niño and to replenish the warm water that was released by the El Niño and redistributed in its wake. Most times, as shown in the top cell, the La Niña replenishes less warm water than was released by the El Niño. At other times, a La Niña can cause more warm water to be created than was released by the preceding El Niño. Here we have a graph of ocean heat content for the tropical Pacific from 1955 to present. The data set is from the National Oceanographic Data Center, the NODC, and it's made up of temperature measurements to depths of 700 meters. And that's perfect, since most of the variations that we've seen take place in the top 300 meters. A little background info. In the early 1990s, NOAA completed the installation of a series of buoys across the tropical Pacific known as the TAO project, with TAO standing for Tropical Atmosphere Ocean. So the data coverage there is reasonably good from the 1990s to present. Ocean heat content data also includes salinity measurements because the saltiness of the water also impacts how much heat it can hold. So that's why the units are in joules and not temperature. As you'll note, I blocked most of the graph with the dialog box. That way we can first discuss the data from 1997 to present that appears to its right. The ocean heat content for the tropical Pacific dropped during the 1997-98 El Niño. It released massive amounts of heat through evaporation. And the ocean heat content rebounded during the 3-year La Niña event that followed it. The stronger trade winds associated with the 3-year La Niña pushed aside the clouds and allowed the sun to replenish the warm water. Notice how the ocean heat content for the tropical Pacific has been dropping since about 2004. The La Niñas have done a poor job of replacing the warm water. So a question for you. With your knowledge of global warming, how long did it take for the warm water to be created that was released by the 1997-98 Super El Niño? Did greenhouse gases cause the ocean heat content to gradually rise in the tropical Pacific? Many people would like you to believe that was the case. Nope, didn't happen that way. The warm water was created during the 1995-96 La Niña. The 1995-96 La Niña wasn't especially strong in the Niño 3.4 region, but the trade winds were very strong in the western tropical Pacific, according to the scientific paper McFadden 1999. The title of the paper is Genesis and Evolution of the 1997-98 El Niño. McFadden writes, for at least a year before the onset of the 1997-98 El Niño, there was a buildup of heat content in the western equatorial Pacific due to stronger than normal trade winds associated with a weak La Niña in 1995-96. The data confirms that. Notice also that the 1995-96 La Niña effectively shifted up the tropical Pacific Ocean heat content. Now that clearly contradicts the hypothesis, the assumption, that greenhouse gases have been responsible for the warming of the global oceans to depths of 700 meters. Did you know that the primary causes of the warming in the tropical Pacific were the 3-year La Niña events and the unusual 1995-96 La Niña? That is, without the 3-year La Niñas and that 1995-96 La Niña, tropical Pacific ocean heat content would have cooled. Since 1950, there have been 3-year La Niña events. They occurred in 1954 through 57, 1973 through 76, and the one we've already discussed, 1998 through 2001. During the multi-decadal periods between those 3-year La Niña events, ocean heat content cooled in the tropical Pacific. In that graph, the 1995-96 La Niña skews the trends, so let's remove its effects. The cooling trend in the mid-period now falls into line with the others. As you can see, there's no evidence of a man-made global warming component in the fuel that supplies El Niño events. Let's expand the data to include the tropics as a whole. The tropical oceans cover about 40% of the global oceans. The primary causes of the warming of ocean heat content for the entire tropics are also the 3-year La Niñas and the 1995-96 La Niña. Between them, the tropical ocean heat content cools. The 1995-96 La Niña also skews the trends for this larger data set, and we can remove its effects. The cooling trend in the mid-period now falls into line with the others, as it did with the tropical Pacific. Again, there is no visible man-made global warming component in the ocean heat content data. One more comment about the ocean heat content data. The NODC has made at least one correction in the last few years in an effort to smooth out that transition to Argo-based data. It still looks a little awkward in places, like this. But more on that in part 2. The last phase of the process is the transition from La Niña back to end zone neutral conditions. La Niña events are also typically tied to the seasonal cycle, so they normally peak in December and January. At the conclusion of the La Niña, the trade winds return to normal strength. The upwelling in the eastern cold tongue region returns to normal, and the West Pacific warm pool expands back to the east, returning to normal. Cloud cover returns to normal. Though not illustrated, there are also Rossby waves returning cool water to the west after a La Niña, but they are far, far, far weaker than those after El Niño events. During the satellite era of sea level data, there have been no Rossby waves after El Niños or La Niñas anywhere close to the size of the one after the 1997-98 El Niño, and we've seen its after effects in that clip from the JPL. Now that we're back in end zone neutral conditions, that doesn't mean the next event will be an El Niño. As we discussed early on, the next event could be another La Niña, and there can be back-to-back El Niños, separated by a year, without a La Niña in between them. Let's discuss one of the not-too-obvious differences between El Niño and La Niña events. As we noted earlier, before an El Niño, most of the warm water that will fuel the El Niño is below the surface of the western tropical Pacific, and it's therefore not included in the surface temperature records. During the El Niño, the warm water sloshes to the east and is now on the surface. It's now included in the surface temperature records. After the El Niño, the warm water sloshes back to the west. Much of that warm water remains on the surface and continues to be included in the surface temperature record. In effect, an El Niño causes instant warming of sea surface temperatures through natural processes. And on the La Niña side, before the La Niña, the East Pacific sea surface temperature is dictated by the temperature of the upwelled waters. During the La Niña, the same thing. The East Pacific sea surface temperature is still dictated by the temperature of the upwelled waters. There's simply more upwelling taking place. After the La Niña, the amount of upwelling simply returns to normal. Unlike the El Niño, there's no leftover cool water that needs to be returned to the west. The flow has always been from east to west all along through Enso neutral and La Niña phases and back again. Two more animations. The first one is of global sea surface temperature anomalies. As you can see, the East Indian and West Pacific Oceans have been highlighted. That's where the leftover warm water from a major El Niño goes at first. This video captures the impact the upward shift in sea surface temperatures caused by the 1997-98 El Niño. And if you'll recall our earlier graph of the sea surface temperature anomalies for the rest of the world, that was the data set that excluded the East Pacific. The data for the rest of the world rises in steps in response to major El Niño events. You're going to watch that happen. The East Indian and West Pacific is one of the primary locations of those upward shifts caused by the Enso process. The graph to the right includes sea surface temperature anomalies for the area highlighted in red, the East Indian West Pacific data. And there's scaled Niño 3.4 sea surface temperature anomalies, our Enso index, in the same graph as a reference for the timing of El Niño and La Niña events. It's the purple curve. The East Indian and West Pacific data is where I first found the upward shifts in sea surface temperature in response to the leftover warm water from an El Niño. That was approaching 4 years ago. My first post on that subject was in January 2009. Okay, enough history. Let's start the animation. Most of the warm water that fuels the El Niño is below the surface of the West Pacific warm pool before the El Niño. During the El Niño, it sloshes east and spreads across the surface of the eastern tropical Pacific, raising the surface temperatures of the Niño 3.4 region and the East Pacific Ocean as a whole. After the El Niño, the warm water sloshes back to the west, where it accumulates at first on the surface of the East Indian and West Pacific Oceans. The leftover warm water prevents the East Indian and West Pacific Oceans from cooling fully in response to the La Niña. Two other things to note. Recall the sea level animation from JPL that showed the Rossby wave. If we watch this video, it does not appear in the sea surface temperature data because that leftover warm water is below the surface. After it collides with Indonesia, some of that warm water migrates into the East Indian Ocean, and some of it migrates north to the area east of Japan. It contributes to the surface warming there as it rises to the surface. Second, notice how the leftover warm water impacts that area east of Japan. That's an area called the Kuroshio-Oyashio extension. Now that was easy for me to say, and is probably why they call it the KOE. That warming of sea surface temperatures in the KOE from the leftover warm water is about as strong as the cooling signal along the equator associated with the La Niña. It opposes the La Niña, and it limits the impact of the La Niña on surface temperatures in the northern hemisphere, not just sea surface temperatures in the North Pacific. That warming of the KOE, which is an after effect of the 1997-98 El Niño, counteracts the effects of the trailing La Niña on the northern hemisphere, land surface temperatures, sea surface temperatures, lower troposphere temperatures, and so on. And that's why those variables do not cool proportionally in response to the 1998-99, 2000-2001 La Niña. And that brings us to the next animation, which is the sea surface temperature data of the North Atlantic. The animation has the same format, except the graph includes the sea surface temperature anomalies of the North Atlantic. Let's start it. An important point. There is no direct exchange of heat or warm water between the El Niño in the Pacific and the North Atlantic. Yet the North Atlantic data warms. You're probably wondering how that can happen. The causes have been known for decades. Changes in atmospheric circulation caused by the El Niño are responsible for the warming. Again, there is no direct exchange of heat. The North Atlantic warms through what are known as teleconnections. Notice how the sea surface temperature anomalies of the North Atlantic also do not cool fully during the La Niña event. That's likely caused by the warming of the KOE, that area east of Japan, that opposes the impacts of the La Niña on the North Atlantic. That concludes the introduction to El Niño and La Niña. It also explained the long-term effects of El Niño and La Niña on sea surface temperatures, so this next section should go rather quickly. But what you did get to see was those upward shifts actually occurring. Those last two animations showed you those upward steps happening. Let's take another look at the East Pacific sea surface temperature anomaly data. In this series of graphs, I've scaled our ENSO index, the sea surface temperatures of the Niño 3.4 region, the purple curve, and added them alongside the East Pacific data, the pink curve. That's simply to confirm that the temporary warmings and coolings are caused by El Niño and La Niña events. The East Pacific warms during El Niño events as the warm water sloshes into the East Pacific, with most of the warm water coming from below the surface of the Western Pacific warm pool. And the East Pacific cools in response to the additional upwelling taking place during the La Niñas. But there is no long-term warming trend. The East Pacific hasn't warmed in 30 years. It's only the temporary home of the warm water released from below the surface of the West Pacific warm pool by the El Niños. Let's take a look at the rest of the world, because it's the more permanent home of that leftover warm water. We know the rest of the world's sea surface temperatures warm in response to major El Niño events. We can see that plain as day. They're highlighted in red in the graph. We've also watched the animations. We've seen it happen. And we've discussed that the long-term trend there is caused by the failure of the rest of the world's sea surface temperatures to cool during the La Niña events that followed those big El Niños. Let's confirm that. We can do that by detrending the rest of the world data and then comparing it to scaled Niño 3.4 data. To help with that graph, let me highlight the periods when the detrended rest of the world data breaks away from, or diverges from, the scaled ENSO index. The two divergences in green are caused by aerosols spewed into the stratosphere by explosive volcanic eruptions of El Chicón in 1982 and then by Mount Pinatubo in 1991. We can confirm the timing with aerosol optical depth data. We can see that the detrended rest of the world sea surface temperature data warm in response to the El Niño events. But contrary to the myth created by proponents of man-made global warming, the detrended rest of the world data does not cool proportionally during the La Niñas that followed the major El Niños. And that, once again, is caused by the leftover warm water from the major El Niño events. As you'll recall, the 1982-83 El Niño was very strong. The reason the shift didn't occur in response to it is the 1982-83 El Niño was opposed by the volcanic eruption of El Chicón in Mexico. Looking again at the rest of the world data with its trend intact, the end result is the long-term warming of the sea surface temperatures there, caused by its failure to cool during the La Niñas that followed the major El Niño events. And again, notice how the data does not warm between the major El Niño events. Let's clarify something, and we can do that by removing the North Atlantic data from the rest of the world data. We're doing that because the North Atlantic has another mode of natural variability called the Atlantic multidecadal oscillation. The South Atlantic, Indian, West Pacific region covers about 53% of the surface area of the global oceans. The sea surface temperature anomalies for the South Atlantic, Indian, West Pacific region show the same upward shifts for the same reasons, but they cool between the major El Niño events. Let's think about that. We know the South Atlantic, Indian, West Pacific region has a long-term warming trend. We know it cools between the major El Niños. We know it warms only in response to the major El Niños, and we know El Niños are fueled naturally. Then that could lead us to conclude that the long-term warming trend in the South Atlantic, Indian, West Pacific region is caused only by the naturally occurring major El Niño events. Summary. The East Pacific represents 33% of the surface area of the global oceans. Sea surface temperatures there have not warmed in 30 years. The long-term warming of the sea surface temperatures for the South Atlantic, Indian, West Pacific region is caused only by the naturally occurring major El Niño events. That region covers 53% of the global oceans. So that's about 86% of the surface area of the global oceans that show no evidence of anthropogenic greenhouse gas warming. And then there's the North Atlantic. It has another mode of natural variability, which caused it to warm at a faster rate than the natural warming of the other ocean basins over the last 30 years. And it covers the last 14%. The global sea surface temperature records show, over the past 30 years, the warming of global sea surface temperatures occurred naturally. That concludes part 1 of the natural warming of the global oceans. In part 2, we'll discuss the impacts of El Niño and La Niña and other natural variables on the ocean heat content data. There was a quick introduction of the impacts of La Niña events on the tropical Pacific ocean heat content in this video. We also took a brief look at the ocean heat content data for the tropics and showed that the primary causes of the warming in the tropics were the 3-year La Niñas and the response of the freakish 1995-96 La Niña. We also discussed that without those 3-year La Niña events and the 1995-96 La Niña, tropical ocean heat content would have cooled. The tropics, as you recall, represents about 40% of the surface area of the global oceans. But did you know the ocean heat content data for the North Pacific north of the tropics cooled until 1988 and then warmed in a 2-year period? It's likely that 2-year warming was caused by a shift in wind patterns, which is typically reflected in changes in sea level pressure. Did you know? If that 2-year period was removed, the North Pacific ocean heat content data would show cooling from 1955 to now. No anthropogenic global warming component is visible in the ocean heat content data we have looked at so far. Everything presented in this video was discussed and documented with data in much more detail in my book, Who Turned on the Heat? The Unsuspected Global Warming Culprit, El Niño Southern Oscillation. A general overview of the book was provided in my blog post, Everything You Ever Wanted to Know About El Niño and La Niña. It includes a link to the free preview and a link so you can purchase a copy if this video has sparked your interest.